Variables are a fundamental and indispensable element, not only in BASIC, but in any programming language, including assembly. Moreover, they are by far the artifact most used by our programs. Everything goes through them, from the number of lives we have left, the points we have scored, where our ships is on the screen, where the enemies are, which keys have been pressed, to whatever you can imagine. Precisely because they are the most used elements and are essential, if we manage to optimize their use, we will obtain higher execution speed and lower memory usage. But let us start at the beginning. What is a variable? It is usually explained as little bots in which we can store values, and we have that bots a name so we can distinguish it. But in really, a variable is a memory space in which we can store values, whether numbers or text. Depending on the type of data we are going to store, it will occupy more or less memory space. This means that we can store, for example, the number of lines we have left in memory, for example, at address 38,682. But since it will be quite complicated to remember all addresses of the variables, BASIC and other languages allow us to name them so we can handle them more easily. Therefore, each of these boxes corresponds to a memory space, where we have the address at which the variable's value starts to be stored and the space it occupies in memory which these two values it is announced in Boriel Basic and in other compiled languages, since the variable name is not stored. Instead, the memory addresses of that variable is used, and this is already a first memory saving. The number of lives we have left, the current score, or the player's names do not occupy the same space. And here comes the first classification, numeric variables and test variables. The former numeric ones can store numerical values, which test variables we store strings of text. Let us see how to Sinclair Basic stores numeric variables. A numeric variable in Sinclair Basic always occupies 5 bytes, whether it is the number of our lives or our score. They are stored in floating point format, which means they lose precision when the value is very large or when it has many decimal places. In addition, as already mentioned, the variable name is also stored. In this case, 5 more bytes since life has 5 letters. How does Boriel Basic do it? Firstly, it allows us to define the type of the data we want to store based on the range of values it can contain, whether it has decimals or not, and whether it can store negative numbers or only positive ones. In this table, we can see the types of numeric variables supported by Boriel Basic, how much memory they take, and the range of values they allow. The most commonly used variables are byte and integer, whether signed or unsigned, as they are the fastest. The rest are used only when necessary. For example, if integer is too small for the score or you need decimals. Fixed uses less memory, but does not have much precision in decimals, although it is faster, as it does not use the spectrum ROM. Float, on the other hand, has more precision, but using ROM slightly penalizes performance. In summary, even if we use float, we are saving memory but not storing the variable name. On the other hand, working with a single byte is faster than with 5, for example. The important thing is to limit the use of each variable, estimate its data range, that is, the limits of the values it will store, and always define them. Let us see an example of the use of limits of variables. This small program called bartest1, which you can find on the official borielbasic.net site, will help us to understand the limits a bit better. In this listing, we define one variable for each of the numeric variable types implemented by Boriel Basic. Then we create an infinite loop using do loop, which is equivalent to placing a label instead of do and a go to instead of loop. In this loop, we print the type and the value of all the variables. Pay attention to the use of the comma. Here we use it to print spaces up to the next tab stop. That is, to the middle of the screen or the end, whichever comes first. The first comma separates the type name from the value, and the second comma prints after the number. If we did not do this, when going from larger value to 0, the remainder of the longer number will not be cleared, and we end with a semicolon to speed up the process slightly. Then we increment the value of each variable, so that the behavior can be seen without waiting too long. One byte variable, byte and ubyte, are incremented by 1 each time. Integer variables, integer and uinteger, are incremented by 10. Long and ulong by 100. Fixed by 100.1 to include decimals, and float by 100,000.1. When running with F5, we will see how the byte variable, when it reaches 127, becomes minus 128. That is, when it reaches its maximum, it warps to the minimum. Ubyte, on the other hand, reaches 255 and resets to 0, as it does not accept negative values. If we had not placed the comma after the variable name in print, when going from 225 to 0, the screen show 055. As you can see, the fixed type has very little precision. We are adding 0.1 in each iteration, but it adds many decimal places, so many that, if you look closely, the text float appears to flicker at times, due to the fixed decimals exceeding the end of the screen. As for float, you will see that the first it shows a single decimal, but when it reaches a very large number, around 100 million, the decimal disappears, it is lost. And if we wait longer, we will see an e plus 8 appears, indicating that the value must be multiplied by 10 to the power of a. Let's use a look at a second example, which you can also find in the borielbasic.net under the name bartest2. In this case, it is a speed test that measures the performance of each variable type. The first thing we do is to define a constant. What is a constant? It's a variable that never changes, so the compiler will treat it specially, saving us the memory space it will occupy. We define this using the compiler directive define, the variable name, and its value. This variable defines the number of iterations each loop will perform to measure time. You can use values from 1 to 65,524, as we will use a uinteger variable as the counter. Next, we define a variable called frames that points to the system variable frames, located at memory position 23,672. This system variable increments by 1 every 20 milliseconds, synchronized with the screen's electron beam. Well, if the screen is CRT, although the spectrum does not care, it increments the variable 50 times per second. This increment is performed by the spectrum ROM on each interrupt, but we will see that another day. Two aspects to consider. First, the frames variable has 3 bytes, but I will only read the first two, the less significant ones, discarding the third, simply for convenience. I can use an integer variable if I know that third byte. The alternative was to be use a long variable, but that uses 4 bytes, so I won't include the value of the net system variable, which complicates the implementation. Second, if we are using a modern machine such as Spectrum Next and Go or an FPGA with a screen frequency of 60 Hz instead of the original 50 Hz, the frame counter rotates 60 times per second instead of 50. So we go from 20 milliseconds to 60.67 milliseconds. We continue with counter. This variable will be used as the loop counter. We will add 1 to each variable 10,000 times, which is the value of match loops, and we will count using this variable called counter. Then, as in bar test 1, we declare one variable for each numeric type supported by Boriel Basic. We print a header with a black background and white ink, and we start with the logs. One for each variable type, all working with the same way. Only the variable and the text printed change. First, we wait for the next interrupt on the screen refresh. We set the frames counter to 0 to reset the clock, and we create a loop from 0 to match loops, in example 10,000. Inside the loop, we add 1 to the variable we are measuring. At the end, we print the variable type and the values of frames, so what we see on the screen is the time it takes the system to count to 10,000. This time is shown in units of 20 milliseconds, so if we wanted milliseconds, we will multiply by 20, but here is not necessary. We repeat this for each variable type to compare which is faster and see the difference between using one or another. For fixed and float variables, we do two versions, one adding integers and one adding decimal numbers. For float variables, I have added an int2 so they print in red. Finally, we switch to blue and print a message indicating completion. Let us run it with F5. We will see it executing, taking slightly longer each time until it reaches float, which takes much longer. From these results, we see that byte variables are 33 times faster than float variables, which is 3,211% faster. For decimals, fixed is 18.5 times faster than float, that is 1,721% faster, although we lose some precision. From this example, we conclude that correctly defining variable types not only saves memory, but also speeds our programs. Now I will explain a typical use with variable limits. Let us look at the program bar test 3, which you can find on borielbasic.net. In this listing, we declare a variable called counter of type ubyte, meaning it accepts values from 0 to 255. We can create a for next loop where counter initially equals 0, and when it exceeds 225, it shows stop and print end of file. The surprise comes when we run the program. Counter loops forever, meaning the loop never ends. This is because the ubyte type only accepts value to 225, so it never exceeds that value, and the loop never terminates. Let us try lowering the value for limit to 224. We will see that it does finish printing the value 224. Another option, if we need 225, is to define counter as integer or uinteger, which allows us to 32,764 or 65,535. We could also replace for with do loop, but that complicates things. Now let us look at variable scope. Boriel Basic allows two scopes, global and local. In Sinclair Basic, all variables are global. Local variables does not exist. How we define whatever variable is global or local? It depends on where we declare it. If defined outside any sub or function, it is global and can be used anywhere, including subs and functions. If declared inside a sub or function, it is local and can only be used there. Be careful. If a local and global variable share the same name, the local one takes precedence. Inside the sub, we access the local variable, but after leaving it, we can still access the global one, which retains its previous value. This can be seen more clearly in the example bar_test4. Here we declare two global variables, varGlobal and varTest, assigning them values 1 and 2. We print their values and call a subroutine called testsub. In testsub, we declare a local variable named varTest, the same as the global one. So inside the sub, accessing varTest refers to the local variable. The global is hidden and inaccessible, retaining its original value to 2. We async 4 to varTest, so the global remains 2 while the local is 4. We do the same thing with global var, but since no local exists, we modify the global. We print varGlobal and varTest, which are now 5 and 4. Once testsub finishes, execution continues and the print both variables again. Running the program shows the first print shows global 1 and test2, the initial values. Then the values inside the sub global is 5, while test is 4, the local value. After test sub, we print again. Global is 5 and test is 2, the global value. Notice the first and last outputs match, ignoring what happened in test loop. Let us see a practical case with the program track, which I will briefly go over. The source code is available on the website. We created a lorry with 3 GDOs plus a 4 blank one to erase the trail as it moves. See chapter 2 for how it works. In main bash, we first set up the GDUs with an include and a poke, so the GDU system variable points to ours. Then we define 3 global variables, each for the lorry's its coordinates, y for the y coordinates, and c for color. Note that the global variable c. We color the screen slightly and enter an infinite do loop. In this loop, we assign a random number between 0 and 23 using RND, which returns a decimal between 0 and 0.999. Multiplying by 24 gives 0 to 23.999. Since y is a byte, decimals are ignored, yielding 0 to 23. We do something similar with C, but between 1 and 7, and use it as the ink color. We then run a for next loop from 32 to -5. Inside, we call drawTrack, which draws the lorry at its, u, creating a movement effect. To slow it down slightly, we added a pause of up to 40 milliseconds. drawTrack accepts 2 parameters, its and u, indicating where to draw the lorry. We define 2 local variables, n as a counter and c to store the GDU code. We reuse names intentionally, including its locally without modifying the global. We assign C to the first GDU code, 144. We run a for loop from 0 to 3. If X is on a screen between 0 and 31, we print the GDU at position X, u. Note that printat uses row y first, then column X. We increment X to the next column and C to the next GDU. The result? A lorry moving left continuously. The key pointing is that drawTrack can be reused anywhere without worrying about variable conflicts. That is the basis of our code reuse. There are still things left unsaid, but for now, this has been a good overview. See you in next chapter.